In this video, we're going to be looking at using multiple integration to find surface area of a closed and bounded region. Now let's scroll down here. So if your the function f and its first partial derivatives are continuous on a closed region R in the xy plane, the area of the surface, given that z equals f of xy over that region R, is, let me zoom in this a little bit, it is the double integral of your region of integration, your dA, of the square root of 1 plus f of x, fx partial squared plus the fy partial squared, where z equals f of xy. Now I have to be careful in the types of problems that I select here, because anytime you start involving integration and square roots, they could get a little complicated, so we'll take that into consideration. So let's come over here and take a look at what we've got here. Let's look at this number 4, where you have f of xy equals 12 plus 2x minus 3y. Your region of integration is x squared plus y squared is less than or equal to 9. All right, that's there are no other restrictions on x and y. Now that's looking circular, so we're likely looking at polar. I'm not saying it couldn't be done in rectangular, but it's I would certainly want to use polar. So I was going to say that obviously once again, if polar applies, you use it when you think it's appropriate. Now be careful. I see sometimes students will do this, when they're doing exams or something like that, is, they don't know what they're taking the partial derivatives of. You're taking the partial derivative of your function f of xy, which is also z. So this could have been given as z equals 12 plus 2x minus 3y. You're not taking the partial derivatives of the region of integration. That's just there to set up the integral. Now, this is not necessary to graph. I mean, you could graph the two-dimensional circle if you wanted to, but I just kind of want to show you this little graph I generated in Maple to kind of give you a feel for what's being accomplished here. So what you can actually imagine, you see I drew the little oblong yellow thing there, is just picture that cylinder cutting through that plane, and then as that cylinder cuts through that plane, what we're actually calculating is the area of that yellow part as the region goes. So like you're taking the XY surface and you're mapping it up to that plane, and it's cutting through there, and then that's what we're finding. Now this one works out pretty well here because the partial derivatives are easy. The partial derivative with respect to x is 2, and the partial derivative with respect to y is -3, which I have written right down here. So now we need to get the 1 plus fx squared plus fy squared, which is going to be a constant because there's no variables left. So basically you have 1 plus 4 plus 9. So the function you're integrating is the square root of 14, a constant. So that makes things nice. So let's see, come down here. So we have a completely enclosed circle, 0 to 3, no restrictions. That's 0 to 3 would be your R, and that would be 0 to 3 no matter what part of that circle. But the key of the no restrictions is why we have then 0 to 2 pi, because that's implying it's going around the entire circle. So that's a pretty easy integral right there, I have to say. That's a good one to start off with. So you're just integrating R dr, which is 1/2 R squared. I'm going to put 3 in there. And that's going to give me 9/2 square root of 14. And then the integral of d theta from 0 to 2 pi. So that's just going to be theta, which will put in 2 pi minus 0, which is 2 pi. Choose cancel. So your exact answer for that area is 9 pi square root of 14. Now this is on handwritten assignments. This is I always specify that I want exact answers. And this is probably the way you would see it on a multiple choice assignment too. You would see the answer choices that way. But handwritten, I like the exact answers. I'm not that concerned about converting it, unless you just want to convert it to a decimal just for your own edification and enjoyment. But that's perfectly fine right there. 9 pi square root of 14. Well, unfortunately, I don't think they're going to all quite be this easy, but like I said, I take precaution into making sure they don't come out to be too. I was looking to see if I graphed this next one, but I didn't. Just kind of curious what that would have looked like. This integral is a little weird. You'll see as we go through it here. Yeah, so some of the simpler integrals I probably won't spend much time with, but one like this has some steps I want to talk about. Well, all right, so there's your function. Here's your region. So we got a triangular region where x goes from 0 to 2, and then y goes from 0 to 2 minus x right there. There's that line, lower to upper, left to right. So we're trapped in that triangle in the first quadrant. And our partials are, there's no x variable here, so the fx partial would be 0, and then the y 3/2 cancels 2/3, subtract 1, so your derivative with respect to y would be y to the 1/2. So we come down here, and then we are integrating the square root of 1 plus, I didn't even bother to put the 0 in there, obviously, because it won't affect anything here. The y to the 1/2 squared is just y, so you have 1 plus y. And I just chose to keep it in dy dx order. I don't know, because the square root of 1 plus y is not that bad of an integral. It's just basically U-substitution. It's when you have like 1 plus y squared when you run into, potential trig integration issues and stuff. But yeah, that's not too bad. So I'll just leave it in dy dx form. And let's see. So what I did here was I did a little u substitution. I let u equals 1 plus y, so that way du is just dy. So there's no adjustments there numerically, any fractions or negatives or anything to pull out there. And I want to change my limits of integration. So I put 2 minus x in there for y. So 1 plus 2 minus x just gives me 3 minus x. Then when I put 0 in here for y, I'll have 1 plus 0, which is 1. So that means u of 0 would be 1. So that now changes my integral. Nothing on the outside was affected here, but we're now going from 1 to 3 minus x. But we're now integrating u to the 1/2 du. And I don't have to go back to variable y. I can get this answer, then we'll do the next integration. So that's just a straight up power rule, u to the 1/2. That's just going to be 2/3 u to the 3/2. And so I'll plug those in. 3 minus x to the 3/2 is just, straightforward as is. Then I have 1 to the 3/2, which I can change to 1. Now we have this 2/3 out here, so what you got to be careful with is that, the 2/3 will multiply by everything through there. You can distribute them separately. So it looks like I decided to create 2 separate integrals here. I think that might make it a little easier. If not, that's okay. But see, the 2/3 belongs to everything. So the first one, 3 minus x to the 3/2, that's just straight substitution. I let u equal 3 minus x. And then du is negative dx, so that's going to bring a negative out here with that 2/3. And, well, you could leave the negative on the inside, but I always like to bring that to the outside. And change the limits. U of 2, 3 minus 2 is usually 1. And I put in 0, 3 minus 0 would be 3. So now I have negative 2/3, 1 on top, 3 on bottom, u to the 3/2. And I guess I should have a du there, shouldn't I? Maybe I freehand that in. I'm not going to worry about making it too nice and neat here, but let's go ahead and put that in there. Oh, not super thick. And not super pink either, or red, or whatever that was going to be. All right. Okay. Okay, let's see. So we have u to the 3/2 du here, and minus 2/3 and then just 1 dx, so that'll be simple enough. So the u to the 3/2 du will be 2/5 u to the 5/2. Now what I did is I reversed those limits of integration to kill that negative on the outside. I've done that in other videos. And so that just reverses them around, makes this positive, so that's going to be 4/15. And we have 3 to the 5/2, and then 1 to the anything is 1. So we have 1 right there. And this integral is just going to be the antiderivative of dx is just x. 2 minus 0 is 2, so you're just going to have 2 times 2/3 with a negative there, makes that 4/3. So we have 4/15, those two fractions, times what's in parentheses minus 4/3. You know, technically that's a good enough answer, really, but I went ahead and distributed it out and got this answer, and then I went kind of another, because I combined, you have a negative 4/15 and a negative 4/3 together will end up combining to be negative 8/5, and I decided to break down that 3 to the 5/2, especially if you were looking at multiple choice answers. You might see it done this way, because basically it's the square root of 3 5 times. Every 2 square root of 3s would make a 3. So you essentially have 3 times 3, which is 9 root 3. And then I went ahead and got what did I do? Factored out reduce that to where, the 9/15 will reduce to 3/5. So it makes it 12/5. So I just factored out a 4/5. So all this stuff down below is just a numerical representation of the same answer, so it's not anything special other than just rearranging the terms. All right. So I made a little comment here, and we wanted to torture ourselves and use polar coordinates. Yeah, keep in mind you wouldn't want to. I just kind of wanted to show you this just so you could sort of kind of get a feel for. Polar, you can take lines, but that's the point. You don't really want to, but you can convert lines into polar. So I can take, y equals 2 minus x, and it's not going to have a pretty representation in polar. So you see I put in r sine theta, put in r cos theta, and, you want to solve for r in terms of theta. So I got the r's over there, factored out of r. So then the 2 minus x would be equivalent to saying 2 divided by cosine plus sine. And then our radical was the square root of 1 plus y, so I replaced y with r sine theta d theta, and that r in front, which I don't know why I wrote it first, but that r in front is the r that goes with dr d theta. I don't know why I did that, but that's okay. I'm not sure. I never actually tried to sit down and work this out to see if it was doable or not. I don't think I really wanted to try, but anyway, Maple figured out a way to do it. And Maple got it, and Maple got the same answer as what we have up here. So, so that means my setup is correct, even if the integral would be pure torture. All right, so now we got a surface area of a paraboloid. So, back in the double integrals in volume section, we might have found the volume of that little paraboloid region right there. Now we're going to find that surface area of that outer surface. So if you took that and smashed it down flat, how much area would that contain? Now, you see this one doesn't give a separate region like these other problems, where it gives the function and the region. It's kind of contained, both here. So with z equals 16 minus x squared, to get your region of integration is just treat z as 0. And then that way you have 0 equals x squared minus y squared plus 16, like I have written right over here. And that's how you handle the region of integration, even though it looks like, so you have a circular base, and we're only, the first octant then in 2 dimensions means the first quadrant. So we only have the first quadrant here. So we take the partial derivatives, and the zx would be negative 2x. Zy would be negative 2y. Yeah, this one certainly has a lot of potential to be done in polar form. So we'll see how that transpires. And let's see. So now you see I have the radical part set up before I worry about converting it.
Those folks from the USSR.
Oh, sorry about that interruption there. Had my TV on pause and it decided to wake up. So, negative 2x, negative 2y, and you put them right in here. So this is kind of your general setup using the surface area formula. Now we have to get it into proper integration. So we have, so there you got 4x squared plus 4y squared. Well, all right, so that's, the region of integration certainly lends itself to being polar, of course. So we have a circle of radius 4, 0 to 4, and then we're only covering the first quadrant, so it would be 0 to 4 and 0 to pi over 2. But also under this radical is a good polar, works, well. 1 plus 4x squared plus 4y squared. Well, 4x squared plus 4y squared equals 4r squared. So now we have 1 plus 4r squared, but see, which looks like it could be trouble, but thanks to our trusty r that we have to put in there every time for polar coordinates, we have r dr d theta, and that's just beautiful. Now we're just set up with a U-substitution integral. So if you let u equal 1 plus 4r squared, du will be 8r dr, u of 4 will be 65, u of 0 will be 1. So I have to bring a 1/8 out of there. Sometimes I write that next line. I didn't here, where I would have written 1/8 du equals r dr. But okay, it's that same 1/8 right there. So the upper limit's now 65. The lower limit's 1. So we have u to the 1/2. So the power rule is going to give us u to the 2/3 right here. U to the 3/2 with the 1/8 still sitting there. And 65 on top, 1 on bottom. So 2/3 times 1/8 reduces to 1/12, and that just gives us 65 to the 3/2. Now I didn't write 1 to the 3/2, that's what it is, but 1 to the 3/2 is 1, so I can just leave that as 1. And now we don't have, so we're just integrating d theta with no other function of theta there, so that's just going to produce a theta. So I you see I don't even hardly show that step anymore. But it produces a theta, so you have pi over 2 minus 0, so it just drops a pi over 2 right in there. So I kind of combined all the terms, and pi over 2 with 1/12 makes pi over 24. And this, where I have this flag, that means that's correct. Perfect, love it, fantastic. But I also wrote it this way, if you're looking at a multiple choice question, possibly on a quiz, on an exam, you might see it written this way. That's anytime you have a 3/2 power, it can always be written as that number times the square root of that number. So, but both of those are mathematically beautiful. They're exact answers. All right, that's terrific. Okay, this kind of goes back to something we did with volume section. It might have been the last 14.3 with polar, because that's what's going to happen here is polar again, where we found the volume that was outside that cylinder and inside this hemisphere. Now we're going to find the surface area of that outer part of that hemisphere cut out by that cone. So it's everything but what's inside cylinder, cut out by that cylinder. So it's taking a hole right through the top of it, and we're finding the surface area of the rest of it. Pretty exciting. So it's hemisphere, half sphere. So there you go. That tells us our radius of that sphere is going to be 5 if we have 25 here. Outside the cylinder, x squared plus y squared equals 4. No restrictions on x and y, so you can pretty much assume we're going all the way around that thing. So I've got a radius 2 there. So this is a little messy here, a little ugly, but it'll kind of clean up here a little bit. So let's kind of Maybe I could have done these, I don't know. I always do the partial derivatives in terms of x and then convert to polar. But anyway, let's just go with what I have here. So so there's the z, to the 1/2, so it's the 1/2 power. So power rule, 1/2, negative 1/2 derivative of the inside with respect to x will be negative 2x. And here I converted it to polar right there. So minus x squared minus y squared is the same thing as minus r squared. And then x is 2 cancels with the other 1/2, and you have negative r cos theta. Pretty much the same thing over here, except you have a y instead of an x, so it becomes negative r sine theta. So now I'm putting it in that square root, which represents what we have to integrate to get the surface area. So I tuck all that in the square root, and let's see if this kind of cleans up a little bit here. So let's see what happens here. When you square this, you're going to have r squared cos squared there, and on the bottom you're just killing the 1/2. So it's 25 minus r squared. Now let's come over here. Same thing here. You'll have r squared sine squared, and then 25 minus r squared. Now let's go back to the 1. What did I do with the 1? Well, notice the second and third terms have the same denominator, so I said, hey, why not make that 1 have the same denominator? So it's 25 minus r squared over 25 minus r squared, so you have common denominators. And look at this little relationship I wrote right up here. With those two, if you factor out an r squared, you have cos squared plus sine squared, which they taught me in trig school, equals 1. So really that whole thing just ends up being r squared. So we have 25 minus r squared plus r squared all over that denominator. So you see it's kind of cleaning up a little bit here. So now we have the r squareds cancel, leaves 25. But now this is still, I just kind of worked the inside part. I didn't permanently get rid of that radical. I just did it without the radical, because now I'm bringing back the radical. So, and here we go. Of course, the square root of 25 would just be 5, so I can factor that, bring that out to the outside. And then this is the square root of 25 minus r squared, which I went ahead, for integration purposes, we're about to do substitution. So I went ahead and lifted that up and made that negative 1/2. And here comes our beloved r that we needed, right? That's always there, whether, we can't not use it, but it's certainly our helpful friend here. So this is going to work out to be beautiful for another U-substitution. So you see, I don't want these integrals to get out of hand on a test or anything. I don't want to turn into a trig substitution or anything like that. So you're essentially just looking at basic substitution on these problems. Now, so we have u is 25 minus r squared, du is negative 2r dr. You put in 0, 25 minus, put in 5. 25 minus 5 squared would be 0. Put in 2, 25 minus 4 would be 21. So we're going from negative, so the negative 1/2, which I didn't show right there, but I think you should know that from Cal 1, makes it a negative 1/2. There's the 5, it's still there. Still 0 to 2 pi here. Oh, and I forgot to mention back up here, let me clarify this. We had a problem similar to this in the section on polar coordinates. So you're not starting, this is one of the rare times it doesn't start at 0, because you're actually going outside the cylinder, which has a starting radius of 2, to the edge of the hemisphere, which is 5. So, does not, that's the only time, well, not the only time, but it's the most common time where it won't start at 0. So I have 0 on top, 21 on bottom. So you know me, I like to get rid of these negatives out here by flipping the limits of integration. And I've talked about this before. You don't flip both of these, just the one you're working with at the time. So 0, 21, flip-flop, 21 and 0. 2 and 2, cancels, 5. So you have the 2 to the 1/2 is the power rule here. So if you do the power rule, you'll get u to the 1/2 divided by 1/2, which was the same thing as multiplying by 2. 2's cancel. And let's see what we have here. Put in 21, put in 0. So 0 won't be anything, so you have 21 to the 1/2, which is the same thing, obviously, the square root of 21. I have the 5 there, now I just have d theta, so I have just throw a 2 pi in there with it. So the 2 pi times 5 is 10 pi. So our surface area is going to be 10 pi square root of 21, whatever square units. So just like volume, keep this in mind when you're working these problems out. Just like you would expect a volume, this is going to be positive answers. So if you got some sort of 0 or negative, you definitely messed up. Now this, like I said, for informational purposes only, I like that. So I just for grins, I just showed you geometrically that the formula for a sphere, surface area formula, is 4 pi r squared. You don't need to know that. But we're doing a hemisphere, so I just put a half of that in front of it. So our hemisphere has a radius of 5. So anyway, 50 pi is what the entire hemisphere surface area would be. And I went ahead and just got a decimal answer here, just so I can compare these two numbers. Normally I would prefer exact answers, but this is just for illustration. So, well, anyway, only point I'm trying to make here is that, which this is not necessary when you're working the problem. It's just to show you this. So there's no doubt. Not only did my answer have to be positive, though, since all we did was take that cylinder and cut it out through the top of the hemisphere, is our answer had to be also smaller than this number. Now, that's, like I said, it's not something you're required to do every time by any means. But turns out 10 pi square root of 21, well, look at that, 143.97. So that effectively that cylinder cut out the difference in area between those two numbers. All right, so I would not worry about that in the least. Now here's one, because evidently the integrals probably, well, I never actually tried this. Maybe I should have, but so evidently if I didn't try it or do it, I wouldn't expect you to compute it. I set it up in both rectangular and polar form, so who knows? Maybe I would have that as a test question, as setting it up, but definitely not rectangular. But anyway, I'm jumping ahead here. Let's look at the partials. Yeah, you look at this problem, you wouldn't even be thinking polar because it's a triangle. 0 to 4 for x, and then y goes from 0 to x vertically. But like we saw earlier, when I had that line, I can make that a line become polar. I'm not always saying it's the best thing to do, but it can be done. So we take the partial derivative of f, which would be 2x minus 3y. Take the partial derivative of f with respect to y, would be negative 3x minus 2y. So you see I square both of those underneath that radical. I FOILed them out. Remember, you don't square the first term and the last term only. You'd be surprised how many people make that mistake. You would think they wouldn't by the time they're in Cal 3, but that's all right. Well, it turns out the 12xy's, well, it's not all right to make the mistake, but I'm not going to dwell on it too much. So those 12xy cancel, so we end up with 1 plus 13x squared plus 13y squared. So in rectangular form, there's your radical. And then you're going dy dx, you're going from 0 to x, and then 0 to 4. So obviously that really could not be integrated, even if you switched it from dx dy. That's not going to help. That really can't be done. But this next one could probably be done if I really put forth the effort, but that's all right. It's because of that limit of integration. It's not this first integral. Anyway, 13x squared plus 13y squared is 13r squared. So you have the square root of 1 plus 13 squared times r dr d theta. Now, here's how we have to integrate this in the polar form. The radius is going out. See, the y equals x means 0 to pi over 4. We've had that come up before in the polar section. So anytime you see the line y equals x, it's going to be halfway through the first quadrant. But x equals 4 can be converted to polar. I think back in my Cal 2 notes I did something like that, but it's not too difficult. You have to let, if x equals 4, to convert this to polar, you have r cos theta equals 4, therefore r equals 4 divided by cosine. Yeah, that is equivalent to secant. So it's 4, obviously, so same answer. So 4 divided by cosine is the same thing as 4 times secant. Either way you want to write it would be perfectly correct. So the issue here is that first integral by substitution would not be that difficult. What would have concerned me, and not having tried it yet, is what's going to happen after you plug that 4 over cosine in there, then to be able to do the next integral. Is that going to be too complicated to do? So that's why I didn't really give it a shot there, but nor would I expect you to either. So that was, it wasn't this first integral. That was easy enough. But then it was what was going to happen after that got plugged in there. So, well, all right, that concludes the video for surface area integrals.